Hello and welcome to our next lesson, which is section 4.2, the mean value theorem. Now we're going to be looking at a little bit of a lead up to the mean value theorem here by starting with something called Rolle's theorem. Now Rolle's theorem says if f is continuous on a closed interval AB and differentiable on an open interval AB, if f of A equals f of B, then there is at least one number C in AB such that f prime of C equals 0. If I think about what this says, I'm going to show you two different examples here. Okay. If f is continuous, okay, on A to B, so I'm going to make this A, make this one B, and differentiable, okay, so no corners, no vertical tangent lines. Here I have f of A equals f of B. What the theorem says is there has to be at least one number C such that f prime of C equals 0. In other words, on my maximums or minimums, this would be a case where we have f prime is equal to 0. So here I have two C's that works for. The slopes of these two lines would be 0. Now the other example we could have is just a straight line. This is A, this is B. Okay. Both of these y values are the same. And no matter where I put my C in between, if I draw a tangent at that point, I would have f prime of C equals 0. So the next part is saying, okay, well, what if I say that it doesn't have to be differentiable? I'm going to remove that requirement. Then I could have corners or vertical tangent lines, which would mean I can't say that f prime of C must equal 0. Instead, I would have that f prime does not exist. So the first corollary here says f is going to be continuous, f of A is going to equal f of B, but I'm removing the condition to be differentiable. And instead of saying that f prime has to be 0, I'm just saying that f has to have a critical number. So that means f prime is 0 or f prime does not exist. Okay? Then the next part is saying, okay, if f is continuous and f of A equals f of B, this is equal to some number d, some y value, right? If the function is above that y value, so what this means, if I draw my function, okay, here's my A, here's my B, these two are equal, f of A equals f of B here, okay? The function is above that, so we can see here, this part of the function is above that, then f must have a relative maximum in A to B. So here I'd have my relative maximum. If our function is below the curve, so if I have something like, I don't know, like this, okay, and it doesn't have to be a curve like this. We could have corners in here. We could have vertical tangent lines. That would all be fine. Okay. Then I would have to have a relative minimum somewhere in that interval. Okay. So the first one says that f would have to have a critical number if we are continuous and the endpoints are equal. That could mean f prime is 0 or f prime does not exist, so a corner or a vertical tangent line would be acceptable. The second part says if your whole function lies above the y value where your endpoints are, then that means you would have to have specifically a maximum. And if you lie below, then you would have to have a minimum. So let's try a question. Find the two x-intercepts of f of x equals x squared minus 3x plus 2. Show that f prime is equal to 0 at some point between the two intercepts. So here we're going to use Rolle's theorem. Okay. If we have intercepts, this means that y is equal to 0, right? There are two intercepts. One of my intercepts would be my A. The other intercept would be my B, okay? So I've got y equals x squared minus 3x plus 2, or x minus 2, x minus 1. which means x is equal to 1 and 2. Okay. Now this would mean that f of 1 is 0, f of 2 is 0, or f of a equals f of b. So as soon as I have f of a equals f of b, my function is continuous. My closed interval would be 1 to 2, and I'm continuous on that closed interval. I'm differentiable everywhere, right? Now I would need to show that there is at least one place where I have a maximum or minimum. So from Rolle's theorem, if f of a equals f of b, or in our case, f of 1 equals f of 2, then there is at least one number c in 1 to 2, the interval 1 to 2, such that f prime of c equals 0. And because we can easily derive this f, we can actually find that c value. Like we could find f prime, then we can find where does f prime equal 0. We can show that that number is in this interval. If you do that, you would get that f prime is equal to 0 when x is 3 over 2 or 1.5. So we could actually find this c value, but using Rolle's theorem, we know that this must be true since this satisfies all of our conditions of our theorem. Okay. Now, the mean value theorem is an extension of Rolle's theorem, but where the endpoints do not need to be equal. Okay, so f of a is no longer equal to f of b. So again, we have f is continuous on AB and differentiable, similar to Rolle's theorem, but we no longer have the condition that the endpoints must be equal. We still have there exists a number c in AB, but now it's such that f prime of c is equal to the slope of the line between the two endpoints. Okay, so what this is saying is if I have my curve, okay, I have my endpoints, they are not equal. I must have a tangent line somewhere in that interval that has the same slope as the secant line between the two endpoints. So the secant line, remember, we would just have rise over run, right? So this is the slope of the secant line here. Okay, and f prime of c is the slope of the tangent line at point where x is c. Okay. So in other words, if I have this curve that's continuous and differentiable on this interval, there has to be a tangent line somewhere on that interval that has the same slope as the line I would draw through those endpoints. Okay. So for example, if I have this function, 5 minus 4 over x, I want to find all c in the interval 1 to 4, such that f prime of c is equal to the slope of the secant line, f of 4 minus f of 1 over 4 minus 1. Now I know that this must exist somewhere because of mean value theorem, as long as this is continuous and differentiable. Okay, so this is continuous unless x is 0, right? That's my domain. X can't be 0, but x is not 0 in my interval anywhere. I'm going from 1 to 4, okay? So I actually would need f of 4 and f of 1 to plug in here. So f of 4 would be 5 minus 4 over 4, or 5 minus 1, which is 4. F of 1 would be 5 minus 4 over 1, which is 5 minus 4, which is 1. So that means f prime of c is equal to 4 minus 1 over 4 minus 1, or f prime of c is equal to 1. So I need to find all C values where this is true, where f prime of C is equal to 1, that are in this interval. So I know I can find f prime of x. First, I'm going to choose to rewrite this as f is 5 minus 4x to the negative 1. F prime would therefore be 4x to the negative 2, or 4 over x squared. Now, based on my mean value theorem here, I'm actually looking for where does my f prime of c equal 1? In other words, where does 4 over c squared equal 1? And this would happen if c squared was 4, or if c was plus or minus 2. Now, I'm not done yet because I was asked all c in this interval such that this is true. And so I'm just going to keep c equals 2 because negative 2 is not in this interval. So you weren't actually asked to use mean value theorem here. They gave it to you. They told you f prime of c was equal to this rise over run. But the other way you could have it is it might say, please use mean value theorem to find f prime of c for the same secant line for these two endpoints here. Okay, and that is all for this section.